Hi, I'm Kate Donahue, and I'm presenting joint work with Alexandra Chouldechova and Krishnaram Kenthapadi on human algorithm collaboration, achieving complementarity, and avoiding unfairness. So to start out with, let's think of some motivating example. In particular, let's imagine a prediction task where a doctor is looking at some patient record and is trying to make some prediction, like say whether the patient has a certain disease or not. In the status quo, this is exactly what happens. The doctor looks at this record and she makes a prediction based on her expertise. But a lot of machine learning research is basically revolving on the question of, can we do better with some sort of machine learning solution? Can we make an algorithm like this that can maybe take the same task and make a prediction with lower error? But a lot of times this isn't the end of the story. It's not just the case this algorithm will straight up replace the human. In a lot of cases, the end result is something like this, where the doctor is using the algorithm to make the final prediction. So she's making a prediction based on this algorithm and also her own opinion and her own expertise. And the question you might think about is, when will this resulting system be better? When will this resulting sort of combined human algorithm system be better in some sense? And obviously the key question is, right, what does it mean for human algorithm system to be better? And we think about at least two different ways you could think of this. One approach you could look at is complementarity. We say that a system achieves complementarity when it has lower error than either the unaided human or the algorithm. So for example, this example on the right exhibits complementarity. The algorithm has an average loss of 0.5. The human has an average loss, the unaided human has an average loss of 0.75. And the human using the algorithm has an average loss of 0.45, so lower than either of them alone. And you could think that achieving complementarity is sort of gives a very strong motivation for the benefits of having this combined system. There's another way we could think of when this human algorithm system is better, and this relates to fairness. So there are two notions of fairness we discuss in this paper. The first is fairness of benefit. And what this has to do is really the benefit of adding in this algorithm to this pre-existing, the status quo of the human by ourselves. We say that something achieves fairness of benefit when all patients see their error reduced when the algorithm is added. And by all patients, we mean sort of like every type of person who could be predicted upon with this algorithm is happier in this system than they were in this system. And another notion of fairness we think about is loss disparity. And loss disparity is basically relates to the sort of disparity in error rates between patients, so between sort of portions of the input space. And ideally, sort of loss disparity for a lot of reasons, maybe sort of patients could correspond to protected groups. Maybe we'd be quite unhappy if there are dissimilar error rates. A nice property we'd like to have is that the loss disparity sort of shrinks when we sort of combine the systems together. It'd be very bad if it sort of gets exacerbated, if there's sort of more unfairness or differential in error rates. But at the very least, we would like to sort of maybe have this be sort of upper bounded by the loss disparity of the inputs here. So here's our setup, and here are the key contributions we give. So we start out by giving a formal and tractable model for analyzing human algorithm collaborative systems. Based on that model, we give concrete conditions when complementarity can and cannot be achieved. Then we use this, we give some results for when fairness of benefit and loss disparity can be achieved. And we talk a little bit about how this interacts with complementarity. So I'll start out by describing some of our model. As I said from the start, we have three components. We have this unaided human, this unaided algorithm, and this combiner, which is the human using algorithmic output. And we have a few assumptions associated with this. I'll walk through them one by one. So the first assumption is that the input space is made up of discrete regimes. And a regime you should just think of as like a type of inputs. And what sort of defines a regime is that the unaided human, algorithm, and combiner have constant error on the same regime. So this basically means that sort of we can decompose the input space into some sort of smallest possible unit. And within each unit, there's constant error. And we're not assuming that we know these sort of regimes, we're just assuming that they exist somewhere. So neither the human knows them or the algorithm knows them, they just exist. The second assumption is that the combined error on a regime is a function of the error of the unaided human and of the algorithm on that regime. So basically think of this doctor example again. So say for a particular regime, say a particular type of health record, the error of the doctor using the algorithm is a function of the error of the algorithm alone, so the error of what the algorithm is giving on this particular type of input, as well as a function of the error of the human alone, so what the human would have said had she not looked at this algorithmic output. And then the next assumption also relates to this. It's saying that the combined error in a regime is bounded between the error of the unaided human and the algorithm on this regime. So this is the error of the output, it's just bounded between the min and max of the inputs. And the reason why we have this assumption is basically to say it's becomes a lot less satisfying if the sort of the output can be arbitrarily uncorrelated with the inputs, right? If you could have sort of, maybe there's an area where the algorithm does very poor prediction and the human does very poor prediction, but somehow both of them together get basically perfect prediction. There are some scenarios where this could happen, but it's helped a lot of our analysis to look at this case where it's sort of there's correlation between the inputs and the outputs. And here's sort of an example explaining all three of these. So we have two regimes here, but of course you could have arbitrarily many regimes. You have the error of the unaided human, the error of the algorithm, the error of the combined system, which is going to be a function of these two. And then we can also say that the error of the combined system is between the error of its inputs. And you can just to emphasize, this last condition does not preclude complementarity, right? The average error here is still lower than the average error of the inputs, even though the inputs on the regimes are constrained, or the error on the regimes are constrained to be within the errors of the inputs. So based on this, we start out by thinking about when complementarity is impossible. And we have some results here explaining this. This lemma says, so complementarity is impossible if any of these are true. At first, it says that the human and algorithmic error rates are constant. And this just means constant across regimes. And this is kind of interesting because this is basically saying, this is why we need this notion of regimes, right? It's basically saying that if you have sort of a flat constant error, you can't in this particular model get complementary performance. You need some sort of variability in error rates. The next condition for when complementarity is impossible is when the algorithm always dominates the human. So when the algorithm always has lower error than the human, or vice versa. And this is also pretty interesting because there are a lot of cases where just say an algorithm is actually quite good. And it could be the case in many real world scenarios that the algorithm is just strictly always better than the human. And this isn't bad by any means, but what this is saying is that this isn't really going to be possible to achieve complementarity in this case. You're always going to do sort of maybe better than the human, but not necessarily better than the algorithm. And the last condition, has to do with the combining function. Basically saying that if the combining function is convex, and then complementarity is impossible. And sort of for intuition, you can think of the function sort of the max of two inputs as convex. Basically, whenever you have sort of a scenario where you're getting larger outputs than your input, you're going to have trouble achieving complementarity. And the reason why we start with this output is that knowing when complementarity is impossible helps us understand when it might be feasible. And that's the next section we turn to. So this is when complementarity is possible. In the full paper, we give an exact condition for when complementarity occurs. And this is in terms of the unaided human's error, the algorithmic error, and the combining function. I'm not going to give the details right now because it requires a bit of notation, but it is an if and only if condition. And it, as you might expect, it relies some on this combining function. So basically a smarter combining function that more appropriately relies on either the human or the algorithm, depending on which is better in a particular regime is important. But it's also sort of interesting, it turns out that highly variable error rates also is important. And so you can think back to our last slide, we said that when algorithmic error rates are constant, you can achieve complementarity. We sort of see the flip side here. For when error rates are highly variable, it becomes much easier to achieve complementarity. And if you're just sitting here thinking about this, right, highly variable error rates, this seems to maybe have some fairness implications, right? A lot of fairness research is about sort of trying to avoid highly variable error rates. And so there is some interaction between these. So the first thing we thought about is fairness of benefit. And again, something has fairness of benefit when all regimes see their error reduced when the algorithm is added. It unfortunately turns out to be the case that any system that has fairness of benefit can't have complementary performance. So these two things are in conflict. And what this is basically saying is that if the overall system has lower average error, then at least some people see their error increase, at least some people who are being predicted upon. I think this is sort of interesting and important to be aware of, right? Just to know that these two things are in tension, and it could help decision makers to know, for example, to know if they're designing a system, which one they should sort of decide to focus on, and maybe try and design a system so that it can help people who are harmed by this system. If there are certain people who see their error increase, if they can be compensated in some other way for this potential increase in error. The next thing we think about is loss disparity. And again, this is the error disparity between regimes. Imagine different people who are getting different patient records who are being predicted upon, and the disparity in error rates between these. The first result we have is that it's possible for a complementary system to exacerbate error disparity. So you have some error disparities for your inputs, and then you end up with a worse error disparity for your output. However, we do give simple conditions for when the combined system will never exacerbate error disparity. And these don't conflict with complementarity. You can have these both at the same time. So just to summarize again, we give a formal and tractable model for human algorithm collaborative systems. We give conditions for when complementarity can and cannot be achieved. And we give some results for when fairness of benefit and loss disparity can be achieved and how they interact with complementarity. If you have more questions, feel free to reach out via email or talk to me during the conference.